I'm gonna explain Lewis structures, and I'm gonna reinforce a little bit more the concepts of resonance and polarity. I'm sorry, resonance, we'll see it on the next exam, but polarity and 3D sketch. Sorry. So let's go ahead and look at the sketch. Okay. What I'm gonna do is that if you learn this, you're gonna have 1 extra point or 2 extra points for that question. Okay, on the exam. 1 extra points. So there's not too difficult. Like you remember the geometry. Let me show you the geometry and the what do we have here? I'm supposed to have the hold on. I'm supposed to have the okay, I know. Okay, on here, okay, we have the, I'm gonna have to put a pause and look for that. I don't know where it is. Okay, here it is. If you look at here, we have how I was telling you, have it on the, you have it posted on Class Jump, and also I gave you a hard copy, very small, but I gave you a hard copy. And I gave you the number of domains, which we already understand what it is. And it's everything that it's around everything, meaning the sigma bond, right? And you know sigma bonds is a single bond. Okay, I can't write here. That's true. So you got the atoms bond, and I call them atoms bonded to the central atom. Okay, for all of you to be able to recognize the atoms, which one are the domains, and which are the atoms, and which are the lone pairs. So if you got two zero, okay, it's a linear molecule. Okay, there's no question about it now, because if you have a single atom with lone pair, it's not a molecule. So the first thing is two with this would be that's wrong here. This would be two atoms and zero lone pairs. So if you have here, okay, three. Okay, if you have three and zero lone pairs, okay, you start having a trigonal planar molecule, trigonal planar band, because you have three around the central atom. Let me draw each one so to give you the example so you understand. Okay, so if you got a molecule which has two domains, like the CO carbon dioxide, you know it would have the lone pairs because we have 12 plus 4, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, okay, and 16. Okay, you have each oxygen, the formal charge is 0. For the carbon, the formal charge is 0. Now, this is a linear molecule. Why? You have two domains only on the central atom. If you would have here a lone pair, which we don't, then it become uh, three domains and it become a trigonal planar. So let me, for a second, sorry, let me erase this. And we'll go back for the explanation on how to use that table. So we got here. This is taking a little bit longer, but it's worth the time. So if we got here this, right, is linear. Now if we got three, and the three domains around the central atom, remember this is the domains, are everything that is around the central atom, and zero lone pair, always when you got zero lone pair, the electron pair geometry is identical to the molecular shape, or they also call it molecular geometry. So it's zero lone pair, trigonal planar, trigonal planar. If from those three domains you got to start being different, the electron geometry, the molecular shape, because you have lone pair. And how I said the effects are different from the atoms around the central atom. So if you got two three domains and two of them are atoms or sigma bonds and one is lone pairs, then you got a trigonal planar, but then the molecular shape starts being different, which is a bent. Okay, now 3, you got 1, 2, trigonoplanar, and the molecular shape is linear. And I'll show you that with the 3D sketch that I was telling you. And as I said, when you got, right, a 3D sketch, if you learn them, it's not too much, okay, you would get, you would get 1 extra points for the question, okay, for the Lewis structure, and it's not going to be very complicated. So if you got an electron geometry, okay, of linear and a shape linear, you just draw it like that. Okay, and this is basically a drawing from a 3D sketch drawing. Okay, to represent the 3 dimensions uh, plane on a molecule. How it says 3D. So you got here the molecular, the electron geometry. Those are the type of trigonal planar you have. Of course, 3 sigma bonds, right? 3 atoms and 0 lone pair. It would be trigonal planar. The word says planar is on one plane. So what do? You have to, and we'll see it with hybridization. You have to draw it. They're not exactly at 90%. Why? Because each molecule, each atom around the central atom has a repulsion between them. And that's called the valence um, electron pair repulsion theory. Okay? That you're going to see on the, let me show you, that you're going to see on an atom. And if you look, you see, so they're explaining what is the lone pair. How do you determine the, like we said, the electron geometry and molecular shape or molecular geometry. If you look at here, this is linear, what I was saying, and this is the molecular geometry would be linear too. And here you got electron pair geometry. I think I jumped the 3, but electron pair geometry, right? And we got 4, 4, 0, 0, the lone pair. So here it is, molecular geometry would be the same as electron pair geometry. But to be sure, you don't look at the PowerPoints. Well, you know, the PowerPoints is to represent the picture and to understand it. But if you got this table, it would be for you better to learn. I'm going to ask you to learn until 4, okay, is our number. So you would have to learn trigonoplanar, trigonoplanar, trigonoplanar bend, trigonoplanar linear, tetrahedral, tetrahedral, you know it's 4, 4, and 0, tetrahedral, trigonopyramidal, bend, and linear. Those are the ones. The other ones, I'm not going to ask you to learn it. We have very limited the time. So we have to look for the best way of learning things and save time at the same time. So trigonoplanar, right, would be this shape. Now, if you've got a trigonoplanar bent, which is how I said, um, 2, remember we're talking about 3 domains. 2 domains are atoms of sigma bond, and 1 is a lone pair. Here it says it's gonna be 2, 2. You got to do the 120, and this you represented on the plane. Always the lone pair represented on the plane. You do not represent the lone pairs on the terminal atoms, just the lone pairs on the central atom. So you get the same instead of B, instead of this B atom, you got a lone pair. So you got your trigonoplanar and bent. If you got a trigonoplanar with 2 lone pair, right? 2 lone pair and only 1 sigma bond, right? You got 1 and 2, that's what it means. You put again this and this, the lone pairs here. You can choose here, but you always have to put 1 atom. So it's gonna be here, here, and this. You'll see you have the same trigonoplanar. Now let's look at the other ones. If you got a tetrahedral, you put the trigonoplanar, the 120 on the plane, but this one wouldn't be a third atom on the same plane. One has to go outside, and this
like triangle means outside the plane, and this one would represent on the back of the plane. So you got the 120-degree, but right, you got on the front of the plane and on the back. Really, what it means, what happens here, is that you're gonna have 109.5 degree between each atom. Trigonal pyramidal is gonna be 3 and 1. It's gonna be three atoms, one lone pair, and at the same, you represent your lone pairs. This is gonna be on the same plane, but this is gonna be up front. This is gonna be on the back of the molecule. Then you have the tetrahedral bent, which is gonna be 2 and 2. So of course, you draw on your plane, you draw your lone pairs, and you got one here and one here. Now, if you got the tetrahedral shape with 1 and 3, three lone pairs, it's going to be linear, right? It's not going to be linear. It's going to be, yeah, tetrahedral linear. So you're going to have your three lone pairs and one only. And that's about what you need to learn. Then you got here, this is what I was representing. The sigma bonds are on this plane. Do you see them? Between the atom. Now a double bond would be here. And this is representing a molecule of ethylene. When you have a double bond here, and then you have HH, HAC. I can write here. Let me see if I can. Okay.
I don't think. Let me see.
Okay, this is this molecule, CH2, CH2, which is C double bond C, and then you have an H2, two bond to this carbon, and 2 hydrogen bond to these carbons. Okay, so that is representing this. As you see, you got this on top and this on bottom. We're gonna see it anyway when we touch hybridization. Then we have here with a triple bond. So for now, just see them because I wanted to show you the picture from that lecture that we did there. So let's look at polarity. Across a period from left to right, electronegativity increases. And remember, it's the tendency of an atom to attract electrons within a bond. It has to be bound to another atom. And up a group is also increasing electronegativity. So here you got, this is why does it? Is because the atomic radii or atomic radius, which would be the same. Now, you're gonna have this table on the exam, which shows that fluorine and oxygen is gonna be 4. Pauling scale assigned for fluorine, right? Let me put a pause for a second. Okay, so let's keep on going here. So I got here, right, the Pauling scale, which assigns the fluorine the most electronegative element, because if it's going up and to the right, it's assigning the fluorine as 4. Then everything is just a comparison between um, the the property that each element has, the electronegativity uh, that each element has. And it's like I said, if fluorine is the biggest one, then you calculate or you get Pauling. What it did is, okay, oxygen would be less electronegative, but this is the comparison between the electronegativity of fluorine to oxygen. As you see, chlorine is less electronegative than oxygen, but it's equal to nitrogen. Okay, now hydrogen and carbon are always same, are even if the electronegativity varies in point 0.4 is considered a nonpolar bond. Let's look at the scales. And if you have the difference in electronegativity is higher than 2, it's going to be an ionic bond. And let me show you. And that's why you form ionic bonds. Because if you have Na and Cl on this side, you have 3 point and 0.9. If you subtract, and remember, we always going to calculate the difference in electronegativity, and that's going to be a absolute value. Our is going to be our dipole moment, what I was calling. So this is going to be, no, hold on, 2.1, I think. Hold on. 2.1. Yeah. So if it's 2.1, look at this. It's higher than 2. So it is an ionic bond. There's no doubt. So Na gives the electron to Cl. Now, every ionic compound is it's higher than 2.0, the difference in electronegativity. This means that. So if you got here a molecular compound, you have the option of being polar covalent and most polar. The less than 2 would be covalent bond. How much is polar and non-polar? There is kind of an section. For example, here is zero point 0.4 and would be a non-polar bond. The rest of them, if it's different from 0, it's around here. Okay? If you have zero point 0.2, zero point 0.1, zero point 0.3, and zero point 0.4, it's non-polar. And 0, of course, because if you have two atoms identical or electronegativity is identical, the difference in electronegativity would be 0. And we know it's a non-polar covalent. But let me check what we have here. And this is the nucleus here, and this around here are the electrons. Okay, if you have symmetrical electrons, it's a nonpolar. Okay, that's what I was saying. If you have a molecule, the total molecule is nonpolar, is symmetrical, it's a non-polar, and that's what we were doing the other day in class. So we got how I explained before, I explained during a lecture this. Bond dipole moment would be an arrow representing an arrow, the direction of the electron, so meaning that the fluorine pulls the electron hard to itself and leaves the hydrogen with a partially positive. Remember, and not completely positive because if not, would be an ion and it would be an ionic compound. So here is the dipole moment, which makes those, if you have an electrical field, the molecules that would have the tendency to attract with a negative charge, the partially negative, sorry, would be on to attract electron, would be on the closer to the positive plate. And this is important to look at intermolecular forces. And I'm still not sure if we're going to have the intermolecular forces in this course. It seems like we don't, but I'll check it out again. I already sent an email. So here we got here, in this case, water is a polar molecule because the vectors converge here and you have two lone pairs. So the resultant dipole moment goes up. Okay, now what it's easy to see is that if we have a molecular an atom which is asymmetrical, right, a molecule, you're going to have a total dipole moment, a resulting dipole moment. Um, that is going to be different from 0, a little bit higher. Okay, remember this is polar covalent, and by the way, water is very polar, so it's 182. It's not 2 because that would be an ionic, but it's 182. And the idea here, like we were seeing on the molecule, right, let me show you this, that if you got water, you got hydrogen here, sorry, you got hydrogen here, you got oxygen, okay, and you got, I'm going to draw it like that so you can see it better. We have here one domain, two domain, three domain, and four. Basically, water is tetrahedral bent. As you see, the domains are different. It's not symmetrical and it's polar. So, of course, the amount of net dipole and how polar it is going to depend on the different in electronegativity between the elements. Then resonance theory, I'm going to give it to you after when we start hybridization. So there's not too much to do here. So the other thing would be, let me just put a pause and I'll be okay. Let me start then with the Lewis structure, and we'll do every single step, okay, like we did in class, but we'll do it with different molecules that we haven't done yet. So we practice 7. Right? If you want, you can stop here the video and just try to do it by yourself and look at the answer. You don't have to go through all of them, but I will explain the first one. So with more time, and as you see, I was listening to other students too, and everybody was And I like that. Everybody was participating. Here I'm going to do it by myself, right? If you have any question, just send me the message through email or instant message through Skype. And for any question, anything you have about this exercise or my Lewis structure that I'm drawing here, the Lewis structure. But anyway, let's go ahead and do it. And we have the first thing is to determine the central atom. In this case, we know already. If you have any doubt, just look at the electronegativity table. It's going to show you that bromine has a less electronegative than oxygen. But anyway, you can see also is the one on the left, which is most of the time the least electronegative element, is the one in least amount. Okay, complicated start when you have three elements on the molecule. So you got here bromine. You got the bromine, and you got one, two, and three oxygen. It doesn't matter how you do it. So you got valence is going to be 7 plus 6, 6 and 6 would be 18, right? Plus one electron, because if you can see here, it has only one negative charge. So this is going to be 18 plus 7, 25 plus 1, 26. So now let's start placing the electrons. We start with 3. That is going to be 3 bonds. That is going to be 6. I do subtract it to have 20 left to play so I can see it much better. So we have 1, 2. Remember, we start with the terminal atom and start placing them 2 by 2, right? Okay, in pairs. So we got 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I knew because it's 6 for each one and it's 3. So we need to place 2 more and we place it on the central atom. Don't change those. Do not touch them later. So let's check our octet. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Now you're going to ask me, why are you erasing and changing this? Because we need to find the best Lewis structure. Okay, how do we do that? Okay, we first find the formal charge on each element, and we have to find the closest to zero because, as I said, Lewis structure is the best Lewis structure is the best representation. Even a Lewis structure is the representation, the best representation that is similar or the best of representation of a molecule, of a real molecule, meaning that if the molecule is sharing electrons and having bonds between them, how can you represent that? You have to represent it on a plane, and this is the idea of the Lewis structure. Okay, so when you got this, and that helps. Why you doing Lewis structure? Because when you got into organic chemistry, if you don't go, it's okay because you need to learn it anyway. But if you go, you're gonna learn that a lot of properties, and even here in this chemistry, a lot of properties are gonna depend on the distribution of the electron. Like for example, water is gonna be a polar molecule. Okay, and water, and you know the properties. Okay, it's an aqueous solution. So the polar molecule is going to depend if you represent the right Lewis structure, you're going to know that you have 2 lone pairs on the oxygen. So we need to do the best Lewis structure. And you'll understand it later when you start intermolecular forces. You understand why we have to do this. So for the bromine, we got 1. Remember, the formal charge would be the valence minus, okay, the unshared electron, which is 2. You don't count them as lone pair. Plus, how many bonds we have? 3. So this is going to be 7 minus 5. It doesn't look too good, this, because you have a plus 2. We don't like those things like that. So we got a plus 2 here. Then you can erase the formal charge. Okay, but I'm going to do Lewis structure, different Lewis structure. Or when we get to the final, then we erase it. And here, oxygen, we already did it in class. It's 6, right, minus 6 plus 1 bond, 6 unshare electron, is going to be 6 minus 7 minus 1. And all of the oxygens are equal, so it's minus 1 minus 1. If you get this, you shouldn't be putting the formal charge, leaving it like that on an exam, for example, because when you represent the Lewis structure, it doesn't go. And I'll erase it then later. So you got here that chlorine. Is this the best Lewis structure? No. Of course, when you add the formal charge, because you put the total number of electron, it should give you minus 1. And adding the formal charge to the minus 1 is a way to check yourself that you put in the right amount of electron. Meaning that if you got, because you're putting the electron, you're placing the electron on the molecule, this total amount of electron. So let's say plus 2 minus 1. Minus 1 is 0. Minus 1 is minus 1. It gives you the minus 1. But it's not, let me write it like that. But this is not the best Lewis structure, or at least we don't know it yet. Because yesterday on the lecture um, we were doing that, and what happens was that when we got to the nitrogen, trying to make it the best Lewis structure, trying to make it 0 on the central atom, it didn't it didn't came up quite well because the nitrogen cannot have was a central atom and cannot have an expanded octet more than 8 electrons. So let's go ahead and look at the next one. Let's try to put double bonds on the oxygen. Some of you will do it directly. I will do it real quick. I will do it real quick, but I'll do it. You leave those electrons here. So what you do is take those electrons for oxygen. You have to take it because the central atom is least electronegative. So you cannot take it away and share them with the oxygen because this is going to give you a negative charge. Believe me, don't do it. Okay, you take it from the oxygens always, or from the terminal atoms. So we got here, okay, 1, 2, 3, 4, 5, 6. We got here for this oxygen, right, which is the formal charge of oxygen here, would be 0. 6 minus 4 unshare plus 2 is going to be 0. I know it already, and you should be knowing it here. So this is the same as we had before, minus 1, minus 1. And this would be 1, 2, 3, 4, 5, 6. And you got formal charge of bromine would be equal to 7 minus 2 unshare plus 1, 2, 1, 2, 3, 4. And still you're going to have 7 minus 6 is going to be plus 1. Oops, you're still going to have a plus 1 here. So is this the best? Let's try because we notice here, and I'm gonna make you this is again minus 1 here because you got plus 1 minus 1 0 plus 0 0 minus 1. So I'm adding the formal charts. That's what I'm doing right now. So if you got here, right, this, we notice that adding a double bond make this 0 and decreases this. So why don't we add a double bond here too? And should take us the bromine for 0. Now, you got here, that oxygen is terrible. It looks terrible. So if you got an oxygen here, and let's add any oxygen you want, you can add it because so except this one. So you got here 1, 2, 3, 4 of oxygen. Okay, 1, 2, 3, 4, 5, 6. So now, okay, we're gonna have here, okay, formal charge for 2 oxygens would be 0. Okay, this is 0. You know it already from the past. This is 0, right? And this would be minus 1 because it stays like that. And then the formal charge, let's look at bromine. It should be 0 because we know it already. 7 minus, we got 2 on share plus 1, 2, 3, 4, 5 bonds to the central atom. So this would be 7 minus 7 would be 0. It seems like it's the perfect one. And I'll tell you the reason. I will go a little bit forward here. So we got 0, 0, 0, and minus 1. We can go more and get formal charge of 0 for everything because we have a total charge. I don't know if you understand that. It's like the assumption, formal charge is the assumption, I'm going to erase them, that all of the atoms are sharing equally the electron. In this case, it's not equally because we have a total charge of minus 1, and that when we add them, we have to have minus 1. This seems, you know already that this is the best Lewis structure. But let me explain you something for a second. If we have this Lewis structure, let's say, let's keep on going with more. So more double bonds, okay? And we have, let's put double bond everywhere, okay? On every oxygen, and this is 2. You got 0, 0, 0. Perfect. What would be bromine? The formal charge of bromine would be 7 minus 1, 2, 3, 4, 5, 6, 7, and 8. Because we have 2 lone pairs, 2 on share, plus we got 6 bonds. It's going to be 8 is going to be 7 minus 8 minus 1. Now, this is impossible because, yes, we got minus 1, 0, 0, and 0. Oh, perfect. You know, no, it's not. Because you can have the central atom, which is less electronegative, with one additional electron, and the ones who are more electronegative with no excess electrons. And you have to have the excess electron. So I'm going to erase all this so not confusing you. I'm erasing it because it's gonna not be, this is the one we're not gonna use for domains and everything. And the same thing, let me get in for a second here. I'm just looking at several scenarios, and look at this. If you go here, right, and you decide to use the central atom, see what's going to happen. By the way, the expanded octet, okay, is going to be, okay, the expanded octet is only going to be valid for the central atom. So you can have from the third period down more than 8 electron on the central atom. Okay, but you cannot have it on the terminal. So don't forget this. So here, and anyway, oxygen doesn't have is on the second period, and you cannot have an expanded octet. And the reason what I'm saying, do not move the lone pairs here. Look at this. This has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is not possible either. So let's work with our best Lewis structure to finish what I was saying, polarity and shape. Okay, and if you draw me the um, the 3D, it would be also extra points. So on the exam. So if you got here, you got one domain. I circle them for my students to visually see it better. Do not count the bonds. You go ahead and look 3 bonds, 3 atoms, 3 sigma bond, and 1 lone pair. Okay? It is a tetra because you have 4 domains. 3 of them are gonna be, right, um, atoms, okay? And 1 is going to be lone pair. So you're going to have a tetra because it's 4 domains, tetra, and you're going to have a trigonal pyramidal, okay? Pyramidal. And if you look at your table, that's it. Now, is it polar? Yes or no? Yes, because you have 4 domains, and there's one that is different from this one. Remember, you don't count the bond. It doesn't matter. You only count the oxygens. You have an oxygen here because when you look at electronegativity, the tendency to attract electrons here is the same even when you have a double or a single or a triple bond. So you got 3 identical atoms, but it's not symmetrical because you have a domain that is different, which is a lone pair. It doesn't matter if that domain would be a lone pair or would be another atom. So yes, it's polar. Okay? And those are the questions you need to be answered.